Okay, so as a quick recap, surface integrals, we're doing some function times the magnitude of RU cross RV. If we have some function where like Z is a function of X and Y, we can use the gradient of G, and we're going to say G is effectively Z minus G of XY. What I've got going on there is G equals Z minus G of XY. When you do the gradient, you get that. If we do that, we can instead write this as F of X, Y, Z of XY. And then we have the magnitude of the gradient of G here. And this will be dx dy. So maybe I'll put a different line right there. Okay, like that. And so and this G is depending on this being Z or XY. If it's the function Y and we're doing X and Z, if G has Y in it, Y of XZ, this becomes dx dz. And if G is a function of X, or G equals X is a function of Y and Z, that'll be dy dz. So that was in our videos. And I'm really bringing it up right now, trying to emphasize that this is one way of writing it, because when we start doing flux in 20 minutes, 15 minutes, this only changes just slightly. Flux is really close to this, which is going to cause some issues in remembering. You're just going to have to remember it. I wish they weren't so similar, but they are. It can aid in memory, but it can also make it harder. Since they are similar, you only have to really memorize one form of this thing. You'll see. So those are the equations we've been working with. Leave that up so you guys write it down if you want to have all your notes for this section in one spot.
What section is this?
This is 15.5.
Okay, thank you.
And we were doing 15.5 on Thursday, but I want to hit it a little bit more, and then we'll dive into flux, because it makes a good transition, doing a little bit of each and showing the difference in one day. So I see Eric still writing, so I'll leave it up a little bit longer. All right, I saw pictures taken, stuff like that. Let's take a look at the problem. So we're evaluating F is Z minus.
Shot. Wait. Forgot the phrasing.
That is so. Let's see. How did I want to do this? Give me 1 second. That's not the full problem. I wrote the problem down wrong. This is not good. Let me grab it real quick.
Hey, Mr. Jones, is that an F vector or is that just a function of F?
Oh, yeah, that's the problem. It's, God damn it, I pulled it from a book that doesn't show that. Ah, fuck it. Let's just make it a vector. And we'll break it. Let's see. We're gonna wing it right now, and this is where things go downhill quickly. So hopefully it doesn't. So
Work for a lot of parking.
I don't know. Let's say z negative x and 0.
Oh no, he's making up numbers. No, no. Don't jinx it, Jericho.
No,
We don't
sorry,
need
it was
another
not-
imaginary
Sorry, it
number.
was not a vector. It was just a function.
Okay.
When we're doing surface integrals, we're not doing vectors. I keep fucking trying to write a vector over it. Z minus x. Oh my god. I've spilled I made coffee, spilled it all over the fucking hall. While I'm cleaning it up, I knocked down a picture frame that's got glass. It shatters. I've had it's been a rough morning so far.
Maybe don't write capital S because that's what's your tendency to write a arrow on it.
Yes, I like what you're saying here. This makes sense to me. That's a great solution, Brandon.
I know I have that. I know I would have that problem for sure.
So let me give you a couple minutes to work on that, and then we'll do it together.
Oh man. Is it just me, or is it really weird that after this week we only have 2 weeks in the final week?
For this class, we're 2 weeks and that it is our final.
Oh, do you guys have when is the final for this
We're
class?
doing it the first week of December. Well, December 6th around then. Let's see. Is this
That's right.
problem going to be friendly? This problem's going to be shitty, isn't it?
I thought it was on the 5th.
Okay, I don't know the actual date. It's the week of the 6th. How about that?
Oh, so you guys
We can go. I'll go look at the calendar right now, just so everyone's on the same
Jeez.
page. We have it on the 5th and the 7th.
are you just offering multiple days for the test, or are you offering
We're,
2
we're
days?
breaking it up into 2 parts.
Oh, okay.
And it's effectively an hour each day. Is it final? I need to give you 2 hours for the final. I will be there early. This is your way of getting more time to do it, rather than doing finals week when you're not going to get that extra time. This is going to get shitty, isn't it? I wonder if we should do ZX.
Mr. Jones, so there's no study guide for this upcoming test, right?
Well, not yet.
But soon, right?
There will be.
All right. Just waiting for it.
No, you're going to wait. You're not getting it until near the end because you guys need to do the fucking homework. Don't just practice the problems that are on the test.
Yeah,
That led to the disaster that happened on chapter 14. You guys got used to my methods of testing and it's not going well.
yeah.
I'm still grading it. It takes a long time to grade it when everyone tries to skimp their way through doing the work. Not everyone. Some people. Don't skimp your way through the homework. Do it.
All right.
All right. Let's see. This is gonna get shitty, isn't it?
What was I saying? That as I do.
Oh no, it's not because it's over the cone. There we go.
Just from 0 to 1. It's not too bad.
steps.
Oh, okay. Do you want to just to make sure, do you want to explain to the class what you just did? Because I can see where you went with it, but
I was trying to let them work. But if they're watching what I'm doing, yeah. I combined like terms. That becomes x squared plus y squared over x squared plus y squared plus 1.
What the face?
because that was not obvious at first.
That's where it is fixed.
Make sure when you're plugging shit in, if it gets squared, the negative gets squared too. Do not write negative x squared because it stays negative. We are squaring a negative number and the thing becomes positive. I've seen a lot of sloppy stuff on tests in that regards. So you want to make sure you do that.
Hey, Mr. Jones, did you do chain rule when you found the partials?
Why?
When you okay, so you have an x up there.
Yeah. This is x squared plus y squared to the 1/2.
Oh, I see. Oh no, I see it. Never mind. I see what happened. Okay, never mind. Because the half and the 2x, the 2 and the that kind of cancel each other out.
We get this a lot. You see this a lot. I figured you guys were comfortable with this by now. We've seen this going to this, I don't know how many times this semester. Maybe not in the form where I've got it written here, but the derivative of the square root.
Where the negative?
That's part of the G equals Z minus G of X, Y.
Yeah.
The other option, I show it both ways in the video. I'm not going to do it right now. It takes 10 minutes to do. The other option you can do is doing square root of x squared plus y squared minus z equals 0. Or going the other way, subtracting the negative x squared over, sorry. And taking the derivative there, that's g. Both of them will get you, oh shit, I did the same thing up there. It comes from, because we want g to be just the function with no, get it all collected on one side. So we collect it all on one side, you do the derivative here. But notice the negative doesn't show up until you move it over. Over here, it's positive.
Gotcha.
It's part of the formula.
It's just another way of doing it.
So without putting in what those boundaries are, we have z minus x times the square root of 2. And this is in dx dy. And since we have dx dy, we don't want to use z. We want to use square root of x squared plus y squared. Now, what are we doing for the limits of integration? Well, z is a cone. When for z equals square root of x squared plus y squared, when x equals 0, z equals the absolute value of y. When y equals 0, z equals the absolute value of x. So it's making a perfect 45-degree angle off the x-axis, and it's a cone like that. And we're going from 0 to 1, which means this goes up to 1 right here, which means this would be this circle right here. If I project it down onto the XY plane, which is what we need, the projection down onto the XY plane, we're getting a circle down here. And it is, z is 1. So if I got 1 equals square root of x squared plus y squared, or 1 equals x squared plus y squared. It's a circle of radius 1. And we're looking at what we're integrating is the cone, the actual barrier of this thing. Okay. So we're actually integrating the cone part. Once we project it down here, though, this right here is just in the dx dy plane. It's a circle. I think maybe we don't need to worry about writing this in terms of x and y, when I think r and theta look a lot more appealing. So let's do that. Let's switch this to r and theta. Theta is going from 0 to 2 pi, and r is going from 0 to 1. And that is r. So we have r minus, if we're going to go to r and theta, the equivalent of x is r cosine theta. We still have our root 2. That's part of the cone portion. And when we switch to polar, we have that correction factor r dr d theta when we got the r as the correction. So let's clean this up a little bit. I've got r's squared. Oh, I could do this is 1 minus cosine theta. Dr d theta. I could separate it when I've done it like this. I can't separate it like this when it's separated, like when it's this part. But now, let me make this clear. I want to show it specifically.
You forgot the root 2. Oh no,
It's up
never
front.
mind.
I want to be very clear, so I want to have everyone's attention for this. When one of these I can write as a function of dr and a function of d theta. The other one I cannot, the way it is. With the minus sign between them, I can't break this up into a dr integral and a d theta on this line right here. That line doesn't transition well. But when I've made it a product like I did up here, this is a function of r only, f of r, and this is a function of theta only, g of theta. I can do f of r and g of theta over here. So that's what I'm going to do. I'm going to have root 2, 0 to 2 pi, r squared dr, 0 to 1, 1 minus cosine theta d theta. That top one can be broken up because it's a product. The bottom one, we can't just separate the r squareds. You can't just strip off the cosine theta. I've seen some weird shit on the test.
Oh, I think you have your bound switched.
I do. Thank you. I would have been going, why are we doing a radius of 2 pi? That's dumb. So this line here is not separable the way it is. I only point that out because I've seen some crazy attempts at separation. Like people tried to shortcut the system without really understanding the shortcut. If you don't understand the shortcut, you don't understand the rules of separation, don't use it because you'll get the wrong answer. It's got to be a product. All right, so I got a root 2. I've got a 1/3 r cubed from 0 to 1. And what did we say about sines and cosines when we're going from 0 to 2 pi? This is going to go to 0 every time. So we've got root 2, we've got a 1/3, and we've got a 2 pi. So 2 pi root 2 over 3. If you're not comfortable with going to 0, do the integral, integrate it. You'll have you'll have theta minus sine theta evaluated from 0 to 2 pi, and you'll see that it goes away. I'd rather you take the long way if you're not comfortable with the shortcut.
The integral cosine is going to be sine, which sine of 0 and sine of hot 2 pi. Yeah,
if you do
the
a
point
U
is-
sub on it, the limits of integration become the same. Cosine, as it is right now, cosine of theta, cosine of 0 and cosine of 2 pi, sine of 0, sine of 2 pi. It doesn't matter which one of those is in here, sine or cosine. This is they get to the same point. So when you subtract them, that part goes to 0. We did this last week. We worked them out one at a time. We showed it. So if you, I'm trying to help speed up the stuff for you, make it more comfortable with you seeing it. But if you're not comfortable with it, work it out. All you got to do to practice it is do the integral 0 to 2 pi of sine. Do it for cosine. And fuck it, do it for tangent. Sine cosine work for any 2 pi increment. Tangent theta only works if cosine theta doesn't equal 0. So we can't do like pi over 2 to 5 pi over 2 for tangent. But you'll see all of these go to 0. And it's something you can use to expedite stuff if you have it learned. If you don't, write it out. Some of you should write it out. Some of you are going, yeah, I knew that before you even said it, Mr. Jones. I figured that shit out in Calc 1. What are you doing with it now? Some people are show-offs though.
James,
I'm not.
did you learn how to do this stuff in Calc 1?
You guys learned how to integrate trig functions in Calc 1. Yes, you did. So I know you did. Whether you recognize this shortcut on 0 to 2 pi is always going to 0, that's a different question.
I think
You just look at it,
Lawrence
you'd
is
be
still
like,
asleep.
Yeah, that goes to 0. I saw sign.
It's the periodic functions. Periodic functions do this.
Wait, no, you can solve that.
Technically.
Yeah, you solve those things in Calc 2.
All right,
You use trig to solve it.
so let's take a look at flux.
I saw like,
I mean,
like,
It certainly wouldn't. It's certainly I don't think it's.
no, it wasn't in an integral, it was just like a
So
parameter.
we just
Oh,
did this for surface integrals. Flux looks very similar. So let's show the difference between the two things right now. Surface integrals, I have F and then the magnitude of RU cross RV. Flux is F is now a function and it's dotted with it. N is also, in case, shit, I didn't write that here. Let me get it in red real quick. N is RU cross RV. So notice these look really similar. I've got F times the magnitude of RU cross RV. And here I've got F as a vector dotted with RU cross RV. When we look at the other form with the gradient of G, I've got F with the gradient of times the normal of the gradient of G. Here I've got it F as a vector dotted with the gradient of G. So they look really similar. Everything is set up the same, except on the surface integrals, the difference is for surface integral, oh, shit, there we go. There's the flux stuff. For surface integrals, F is a scalar function. And we're doing the magnitude of the gradient of G or the magnitude of RU cross RV. Let me do this. There, now I get more on one page, one screen. That's surface intervals. When we do flux, they like to use the nice fancy looking phi. I think it's a capital phi. Here, F is a vector field. And we're not doing the norm of G, we're just doing the regular G, gradient of G, or the regular RU cross RV. So they're close, they're similar, which you can use to memorize the structure easier as long as you can separate the difference. Fluxes for vector fields, surface integrals are you're just finding the value over the surface. The idea of flux, real quickly, for those that didn't watch the video, whether you've got some pipe and water's coming out the end, we've got a vector field of fluid throwing to the pipe. Flux measures the amount of fluid that goes through a surface. So if I put like a fine screen over the end of this.
Bernoulli's equation.
Yeah, that's what I thought of too. Like,
Yeah.
What?
Bernoulli's equation. It's water going through
Yeah.
a surface. Yeah.
It measures the flux is the fluid flowing out over
Yeah.
a unit time. mass of the fluid over your time. Okay, this also electrostatics. The electric field going out is going radially out, and here the surface was a plane. On this, we might make the surface a sphere around it. And how much, what's the electrostatic charge there? How much is flowing out from the positive charge?
You got your physics for the math from the math class now. You're happy, right?
Yeah, but we skip all this shit. It's actually like, we don't even talk about most of the stuff. It's just kind of like, you do this, and then this happened.
Isn't that the point of reading the book then?
Read the book. This guy.
So that's what we're doing with flux. And these are the two differences between the surface integral formulas and the flux formulas.
Seriously.
You didn't read the book. Why would you not read the book? That's where the concepts are. Learning the math there.
I cover a lot of the concepts in the videos if you watch the videos. I talk about this as well. This is Gauss's theorem.
Gauss. Was
Theorem?
ousted?
Isn't it Gauss? I think
It is.
Gauss was a great man. Maybe that's the divergence theorem. Divergence theorem.
Yeah.
Next section is Gauss's theorem.
Hence his name.
Yeah, divergence theorem is Gauss's theorem. My bad. All right, so we're gonna do that problem that's listed right here. I'm gonna write it on another board so I don't have to erase that. And then I'll swap the boards. So we're gonna find the flux of F across the surface S. F equals xk. S is 0 is less than x less than 2, 0 less than y less than 2, and z equals 0. So my graduate work was on magnetic flux. In particular in the sun, in a star. Tubes of plasma have different magnetic properties, and those magnetic properties cause it so that the flux it stays in its tube. The tube will move around, but since the way that the structure is, the magnetic field just keeps the shit together, so there's no flux outside the ends of the tube or out the barrel. There's no flux this direction for magnetic flux. It's only along the tube, as if there was a pipe there, but we know in the sun there's no pipe. It's just a bunch of plasma moving around. So mine was on magnetic flux. So I did my graduate work in applied mathematics was really astrophysics. So you could study other stuff than mathematics while doing applied math. This is what I was telling James and Eric and Lawrence, and I've talked to some of you on Discord if you're reading it. If you're interested in those fields, you can study all that while getting a degree that's marketable everywhere. Every business uses a mathematician of some form or another. All right, so let's take a look at the problem. F equals xk. So F is 0, 0, x. And S is this plane right here. So it's a region in the XY plane. So the normal vector here is straight up. It didn't, if it doesn't mention an orientation, assume orientation is positive, going in the normal positive direction. So that's my n, which means n is 0, 0, 1. And flux was f dot n ds, is the root form of it, the most basic version of it.
It stands for flux.
But the uppercase. That's not just uppercase something. It's, yeah, it's just typically symbol.
Wait, what did you say that symbol was?
That is something. Uppercase.
I believe it's capital phi.
Capital phi.
Like,
Really? Oh, now that I think about it, yes, that does.
Doesn't it look real similar to phi?
Yeah, yeah. I can see what you're talking about. Huh.
90 degrees. That makes symbol.
So I've got my f dot n ds. F dot n looks like it's just x, right? Remember, we're left with a scalar value after a dot product. It's not a vector anymore.
Mr. Jones, can you see how you got F first, really quick?
It says x is in the k hat direction.
Oh, I see. Okay, got it. Thank you.
Which means 0i plus 0j plus xk. They could get tricky like that.
They do tend to get.
And I never know who you're going to work with in the future, so I want to make sure you're comfortable seeing both. I know I like this way better, but let's actually in this problem, xk hat is a lot shorter to write than the vector like that. Huh. Usually this is the longer form of doing it. But that's my f dot n, so we need to throw that in the integral. So we're doing the integral of x ds. Well, what's x? What's ds? It's this surface here from 0 to 2 for x and y. So we can do 0 to 2. Let's say x, 0 to 2 of y. We've got x, dy, dx. Now, if you want to recognize this as a product of 1 and x, this is separable. Or we can just work with it normally.
Absolutely. I thought those were Z's. Oh, I told them. Zero to zero.
So we should get 4 for that.
Being four or what?
Just 4.
4 looks units. Water's going through that surface on a board.
Just 4. I mean, that's all you got to tell building manager. Just 4. That's what my calculation got. Just 4.
Collaborative. Kind of like figure out how much heat is escaping a room or something. And then how much NVQ do you
You guys ready for another one? That wasn't too bad, was it?
Not why this. Right.
Oh, the thing I was talking about with the magnetic flux is what causes solar flares.
Going to the surface of heat.
Where
Wait, say it
the
again.
magnetic flux causes pressure differentials in the stars, and the tubes of plasma, the magnetic flux causes lower pressure, or can, and which will cause the plasma tube to rise to the surface and shoot up, so you see the solar flares. So that was kind of a neat application in grad school.
Solar flares form.
You calculate.
That's magnetic flux. We're not doing magnetic flux. We're doing regular flux.
Lauren says
Really
he
not a
wants
lot
to
of
do.
difference. Magnetic flux is the B field.
Lauren says he wants to do magnetic flux in his free time. You looked very disappointed.
I don't know what that means, but it sounds inappropriate.
Wait, what?
You want me to magnetic flux your free time? I don't know what that means. But flux sounds like
And you
Well-
window.
don't hit on me, Lawrence. I don't care what your affiliation is, but I'm your teacher. You can't do that.
When did your sexuality have to be an affiliation? I didn't
Yeah,
know
that's
this turned
an
into a
organization.
company-wide thing.
All right. So what do we got here? Let's look at the surface. The surface is in the XY plane, or the Y. It's in the X and Z plane. Because Y equals -1 is right there. So we're going up 4, down 4. This is Y equals -1. X is 2. Oh, wait, not down 4, just a 0. So this is 2, and that's 4. Let's just rewrite this another way. Why don't we just break the height up evenly? That's in half, that's in half, that's in half. Okay, so Z equals 4, X equals 2. We've got Y equals -1 there. This is the Y equals -1 plane. And it says it's oriented in the negative Y direction, which means that N hat is that direction. Which means N hat, or N, well, N hat too, since it's got a vector or magnitude of 1, should be 0, -1, and 0. Since Y is not changing there, F is really X squared, X plus e to the -1, -1. So F dot N, we've got X squared, X plus e to the -1, and -1, dotted with 0, -1, and 0. So we'll have 0x squared minus X plus e to the -1 plus 0 times -1. And I realized some of those 0 out, but I didn't just want to jump to it. Not everyone's stellar at dot product yet. So my F dot N is -x minus e to the -1. And we have our bounds given to us, 0 to x, or 0 to 2 and 0 to 4. I could put the negative out front and leave this as x plus e to the negative 1. And I've got dx and then dz. Today we're just doing f dot n. Tomorrow we will do the other forms, f dotted with ru cross rv, or the gradient of g, where we've got functions of z and stuff like that. But I want to ease you into flux. This is not separable. Well, I guess it technically is. Yeah, it is. This is just constant with respect to z, so I could separate this. I could do negative 0 to 4 of 1 dz, and then 0 to 2 of x plus e to the negative 1 dx. So there is a plus sign in there, but there is no other variable. So I can put the entire thing with dx. I cannot break that up and put part of it with dz. So if there's a plus sign, it's all got to go to the same integral. So we've got, what do we got? We got negative z from 0 to 4 times, we got 1/2 x squared plus e to the negative 1 x from 0 to 2. Two plus 2 e to the negative 1, and then 0 and 0. So we got negative 8 times 1 plus e to the negative 1. And I am pretty pleased with the way I compared flux and surface integrals today. I'm going to take pictures of them and put it on Discord, so you can see the side-by-side comparison there if you didn't take a picture or write it down well earlier.
I'll be holding my regular SI hours later today. I won't be very available this week if you're trying to reach me through Discord though. Yes, question?
Does a negative flux mean that like something is flowing into it, like just the fluid example?
Did you hear him?
I did not. I heard something about negative flux.
So he was wondering if the fact that you're getting a negative answer, how that changes the flow.
It means it's flowing to the left.
Oh, it means it's flowing to the left instead of the right.
Wait.
Because he's wondering.
But no, it's flowing to the right because the normal direction is going the other direction. So the flow should be going to the right. It should be going in the positive y direction because the flux is negative. Which makes sense. Our flow field up here is positive in the y component. So it should be going to the right.
Or is it part of the light? Or wait, is that the direction?
So it's to the right. This means, so for a better way of saying it is a negative flux means it's the opposite direction of n. So here it's flowing to the right.
All right, see you later.
I'll see you guys tomorrow.
Yep. And only tomorrow too.
Well, I will be doing stuff Thanksgiving week at Starbucks if anyone wants. We'll talk about it tomorrow.
Double check.
I will see you guys later.
Oh, this is right. Okay.